In this video, I simply want to give an overview of unitary matrices and some important properties of these matrices. In particular, let's call U hat, so this is a unitary matrix, and we can write it in the following form, e to the I h, where H is a Hermitian matrix, and the matrices U form the group SU of n, where n is the number of rows and the number of columns of U. So these are the special unitary matrices. H is Hermitian, so it satisfies the following equality. Hij is equal to H star Ji. So there are some constraints on H, and out of the n squared complex parameters which form the matrix U, or also H, we will get from these constraints that we have n squared real parameters for H and also for U. And we also know that U dagger U is equal to the identity operator. So this operator here, the dagger, is simply the complex conjugate transpose. If we take the determinant on both sides here and also we take the, the square root of that, what we get is that the mode of the determinant of U is equal to 1. So in particular from here, if we take the determinant on both sides, we get determinant of U mod squared is equal to 1. So if we take the square root, what we get is this equality here. And in particular, sometimes I might miss writing these hats, but it's not really important. So there is no risk of getting confused if I write U or U hat. So let's write U hat. I will try to stick to this notation, but if I miss some of these hats, please do not get confused. And also another important property is that the trace of H is equal to alpha, where alpha is a real parameter. It's a simple property because H is Hermitian. And also the determinant of U is equal to the determinant of e to the I h, and this is equal to e to the I the trace of h. So in this case actually we can give a proof to this fact, and in particular let's start from I h. I'm going to rewrite it as lambda I d lambda inverse. So I'm going to rewrite IH like this, where D is a diagonal matrix, and it's easy to understand that e to the I h, which is by definition the summation over n from 0 to infinity of I h to the power n over n factorial, this is equal to lambda e to the I d lambda inverse. It's quite easy to realize because you can write the series representation of the exponential of this product of matrices. So you have e to the lambda I d lambda inverse. So you have the summation from 0 to infinity of lambda I d lambda inverse to the power n divided by n factorial. But now, if you write all these products, so you have lambda I d lambda inverse, this multiplies lambda I d lambda inverse, and so on and so forth. You get the idea. You have to multiply it n times. You can see that in the middle all these terms will cancel, so they will give the identity operator. So at the end of the day what you get is this, when you of course make the summation. And therefore from here, if you take the determinant of e to the I h, this will be the determinant of that, of this. So when you have the determinant of a product, you have the product of determinants. So you have the determinant of lambda times the determinant of this times the determinant of this. But the determinant of lambda is equal to the inverse of the determinant of the inverse matrix. So the product of these two determinants will give you 1. And you will be left with the determinant of e to the id, like this. But now this is a diagonal matrix. So it's quite easy to compute the determinant, and you will easily understand that you will get e to the I, the trace of D. Now another simple thing to see is that the trace of D is equal to the trace of lambda D lambda inverse, and it's quite easy to prove by using index notation. So if you write this by using index notation, you can easily check that you get this equality. So let me do it. So you can write it as, for example, lambda ij dj k lambda inverse k. Let me use s as another index. So you have to sum over j and also over k. And then what you can do here is the following. So since you have to take the trace of this, you also have to sum over I and over S. So it means that I and S will be the same. So you have to sum over these two indices. It's as if all these were multiplied by the Kronecker delta IS. So it means that we can replace S with I. And now, of course, we can rewrite this as lambda inverse Ki times lambda Ij djk. But here we have delta Kj, and delta Kj times djk, since D is just a diagonal matrix, this will be the trace of D, right? So basically, we have proved that this is equal to e to the I trace of lambda D lambda inverse, or if you put an I here, of course you get the same thing. You can put an I here, and therefore here you have e to the I trace of, or you can put I inside the trace. So basically here you can write this as the trace of lambda id lambda inverse, but this is just I, H, and I managed to prove this result, and this is equal to e to the I alpha from here, and alpha is a real quantity. So the determinant of u can be written like this. So if you take the magnitude of this, the magnitude of a phase, so this is equal to the square root of cosine squared alpha plus sine squared alpha, right? So this will be just simply equal to 1. And these are very useful properties of this kind of matrices, these unitary matrices. And then let me add more, let's say, insights. So if alpha is equal to 0, then we know that the determinant of u is equal to 1, because it is equal to e to the I alpha. But if alpha is 0, of course, you get 1. And this group of matrices is called the special unitary group. So it depends on n, now because we are considering n by n matrices, and this word here, special, is used when alpha is equal to 0. Otherwise, there is the more generic word u of n. So it is just unitary but not special. So I've also used the word special earlier, but I was actually referring to the group such that alpha is equal to 0. So where h is traceless. So it is the group where h is traceless. The trace of h is equal to 0. Now we have n squared parameters, as I said, real parameters. And with the condition that the determinant is equal to 1, or just a phase, we have n squared minus 1 parameters. And let's now consider a group element u belonging to the unitary group of n, and it is a function of n squared parameters, and let's simply define n squared equal to n, lowercase n. So u will be a function of some parameters, and I will call these parameters phi 1, phi 2, dot dot dot, phi n. And this can be written as an exponential, and we will define the exponential like this: e to the minus I summation over mu phi mu L mu. I could also use the summation convention, so I can rewrite this as phi mu L mu without the summation, or for simplicity just phi times L. So by this I mean phi mu L mu, which is exactly equal to that. And the parameters L mu are actually quite important, and I want to stress the importance of that. So at first you can see that minus I L mu is equal to the derivative of u with respect to phi mu, and then we evaluate it where phi is equal to 0. And phi, by phi I mean phi 1, phi 2, phi 3, phi 4, phi n, they are all equal to 0. Now when these parameters phi 1, phi 2, phi n are small, and when they are small I will simply replace them with delta phi mu, for example, this matrix U can be simplified, and it will be approximately equal to 1 minus I summation over mu from 1 to n delta phi mu L mu, and then you might have higher order terms that I will not write. But now what I want to do is I want to find some relations that these operators L mu have to satisfy for the group. The L-Mus are called the generators of the group, and they will have to comply with some commutation relations that I want to derive. So let's first define other parameters like alpha, and we will define alpha L, and this is by definition alpha mu L mu. So these are just parameters like the phi's, phi 1, phi 2, phi 3, and so on and so forth. But in this case, I will simply call them alpha. And when I write beta L, I simply mean beta mu L mu, where I defined other parameters and so on. So the group should be closed. And what I mean by that is that if I consider e to the I alpha L times e to the I beta L, especially when alpha and beta are small, it's quite easy to understand that this will be equal to e to the I delta L for some delta that is not defined, but it will depend on alpha and beta. So this is called the closure property of the group, and it's quite important. By the way, we can also think of e to the I alpha L or alpha mu L mu as the limit as k goes to infinity of 1 plus I alpha mu L mu divided by k to the power k, like this. Now, we can rewrite I delta L as the logarithm, or if you want, you can write ln, natural log, of e to the I alpha L, e to the I beta L, and we can rewrite this as the log of e to the I alpha L times e to the I beta L minus the identity plus the identity. We are going to rewrite this as k. When alpha and beta are small, all the coefficients are small, then k will approach the zero matrix. Now we can expand this by using the expansion of the logarithm as k minus 1/2 k squared plus k cubed over 3 plus dot dot dot. If you take a look at k, which is equal to this expression, we assume that alpha and beta are small, we can rewrite it as 1 plus I alpha L plus dot dot dot. This multiplies 1 plus I beta L plus dot 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 minus the identity. Now you can rewrite this by considering some terms. When you do the multiplication, you get I alpha L plus I beta L minus alpha L beta L. And then if you consider also the second order terms here, when you multiply them by 1, you get minus 1 half alpha L squared minus 1 half beta L squared. The minus comes from the I, right? The factor I plus dot dot dot, and then you can replace k here. You can put k there, so you have I delta L, which is equal to k minus 1 half k squared plus dot dot dot, and this will be equal to, so when you consider k, you have I alpha L plus I beta L minus alpha L beta L minus 1 half alpha L squared minus 1 half beta L squared plus, and then you have minus 1 half k squared. And in k squared, I'm just going to consider these two terms because all the other will give higher order terms. So we'll truncate everything to the second power here. I have I alpha L plus I beta L squared. And when you do the algebra here, I delta L will be equal to I alpha L plus I beta L minus alpha L beta L plus 1 half alpha L beta L plus 1 half beta L alpha L. This can be written as I alpha L plus I beta L minus 1 half, and then you have the commutator alpha L beta L like this, which you can recast in the following form. So this is equal to I delta L. You can write commutator alpha L beta L equal to minus 2I delta minus alpha minus beta L. And if we rewrite the indices, here we have commutator alpha mu L mu beta nu L nu equal to minus 2I delta gamma minus alpha gamma minus beta gamma L gamma. Now we are going to rewrite this. We define it to be I alpha mu beta nu F mu nu gamma. And from here we get the following. So the commutator L mu L nu L mu L nu is equal to I F mu nu gamma L gamma. And lo and behold, this is exactly the commutation relation that we wanted. And in particular, this F mu nu gamma is simply called the structure constant. So when we vary mu, nu, and gamma, these are the so-called structure constants. And for 2 by 2 matrices, this will be related. So by this, I mean these L nu and mu, they will be related to the Pauli matrices.